Okay, so today we will be continuing on what we started last week. So last week was going back to the single degree of freedom system, where at the start we talked about forming the equation of motion. Then we start talking about some dynamic properties. That was week 4. Then week 5, we started imposing some harmonic motions into the system. We now understand the differences between damped and non-damped systems. So this week we're going to continue on seeing some special behaviors related to the harmonic excitations, and also we're going to learn some tests that can happen from applying such excitations. And the other thing is, last week we stopped at carefully talking about the deformation represented by displacement response factor, the RD property. Remember, last week we spent a lot of time talking about the RD property. What was the RD ratio between what and what, if you remember? Anyone? The RD was ratio between, or the displacement response factor. Yes, so that was the ratio between the dynamic displacement and the static displacement, basically. So this week we will be talking about velocity, and we will be talking about acceleration. It is kind of the same definition. Velocity response factor is the ratio between the dynamic velocity and dynamic displacement. Acceleration, same thing. It's the ratio between dynamic acceleration and static acceleration. Static means we're just not considering the inertia input into the equation. So typically the dynamic should be higher because it's involved some inertia actions inside. Okay, so we're gonna look at these 3 properties together this week and see what they can give us in terms of relationships that can help us to solve some real-world problems. We're gonna see some new tests today, which we can apply and use those theories to help us determine the properties of existing building, same as what we did in the previous week or weeks as well. So looking at equation 14 and 18, that was from last week. Last week we had things defining the RD property, which is the displacement response factor. So what we did, we differentiate the equation 14. So we differentiate equation 14. We stopped out last week. Eventually it will give you, if you differentiate displacement, gives you velocity. If you differentiate it for another time, it will give you acceleration. So for now, we just differentiated once. You're going to see now the equation going to be adjusted where it's going to be defining velocity, and we will have something defining the RV, not RD anymore, which is the velocity response factor as written to you here. And the RV can be related to RD, we talked about last week, by this ratio. Right, now that's what I'm showing you here is a summary of the equations we will be using, and that what you need to know how to use, and that will need to be written on your formula sheet that you're going to prepare for the final exam. Right, I will not ask you to show me a derivation for each formula. The derivation is all about math processes, which you can more than welcome to look at that reference textbook to look at. But I just want to really extract what can help you to apply some dynamic theories to solve dynamic problems on buildings. So far what I'm telling you is there is a relationship between RV and RD and can be related with those properties That was the frequency, the forcing frequency, which coming from the harmonic motion over the natural frequency, which is, it depends on the structure we are studying or investigating. So then further differentiating equation number 15, it will simply give you this adjusted formula, number 17. And again, we will be able to determine the RA relationship with RD. So there is a mathematical relationship between RA and RD. And as you can see, it's same as, it's just the power square for the relationship, for the ratio, the frequency ratio, forcing frequency over the natural frequency. Here it was just unpowered, and here it was powered to the to 2, which is coming from the deviation. Right? Now, from there, we similar to what we did last week, we are able to use these equations. We take them in Excel file and start plotting charts and varying the frequency ratio in the horizontal axis. We are changing the frequency ratio from 0 to 3. And in the vertical axis, we got the 3 parameters I've just defined for you. So first one is the displacement response factor or deformation response factor. This one, velocity response factor. The third one, it is the acceleration response factor. They are all plotted in function of the frequency ratio in the horizontal axis. So the main thing you need to note, and what I'm really highlighting to you in terms of noting, it will be the items used in solving the problems we are going through. In terms of the examples or the workshop questions. So there are items which I am highlighting on. They will basically help us to see which pathway to go with. So for example, here, we just need to find the special features of each. Looking at the first one here, RD, that was something we discussed last week. Pay attention to where it's peaking. Pay attention to where it's peaking. We're going to come to it. So what we found is when the frequency ratio is at unity, when the frequency ratio is 0, so have a look to here, that's when the frequency ratio, we said the horizontal axis is the frequency ratio. When the frequency ratio is 0, then the RD will be 1. We talked about this last week as well. Now, the RD will be peaking, not at frequency ratio being 1, it's a little bit before 1. So that's what we're saying here. When the frequency ratio is less than 1, somewhere here, then the damping or the RD value, deformation response factor, will be reaching its peak. So it's not peaking at 1 response frequency ratio, it's peaking just before 1. That's why we're saying less. Now, when the RD value is approaching to 0, that's what's happening with it. It's approaching to 0 towards the right. It's approaching to 0. You can see here. Then we will be able to have the frequency. That's where the frequency ratio is heading towards infinity. When the frequency ratio is heading towards infinity, that's where your amplification for displacement will be kind of none. So you can always see there is any amplification. So that's the story behind what's happening with the displacement response factor. On the other side, talking about the velocity side, where we got the velocity response factor, RV, things will be slightly different. So the RV value will be 0 when the response ratio is 0. So obviously, when there is no forcing frequency, always think about the practical, the real behavior. So when the response ratio is actually 0, when the response ratio is actually 0, which is, what does it mean? We're always going to have a value for the natural frequency. You agree? Because you're always going to have a structure with a stiffness and with a mass. So because of that, we're going to have W, always, Wn. or sorry, omega n, should say, omega n. Now, if we don't have any load, obviously, on a structure, which is exciting a structure, that means the ratio is 0, then obviously that means the RV value gonna be 0, which is obvious. There's no velocity response factor. Now, the velocity response factor will be at its peak when the omega omega ratio or the frequency ratio is 1. So when we have resonance, we definitely should have the omega peaking, but that's now not before 1, it's exactly at 1, right? So usually the RV value will be 1, not less than 1, so it's going to be at its peak when it is the omega, the resonance is actually happening. Now, same thing with what we've seen before with displacement. As we go to infinity, the RV value will be approaching to 0. So as we go forward away and away, it will be approaching to 0. So same as displacement, but the displacement was much faster approaching the 0 than the RV value. Let's see the third situation. So here I'm just highlighting some main behaviors. How are we going to use that? It's going to happen in your problem. Your problem, you're gonna be knowing when you test something, you're gonna determine where is the peak, where is it approaching 0, where it is approaching 1. Because when you do a test, basically you're gonna plot a curve like this. All right, now I'm taking you through those theories. Someone will say, how I'm gonna use this in real application. I just want to explain to you what each parameter means and how it's gonna be translated in terms of discussed when you read your problem and understand it. Because with any test you do, you're going to be plotting these curves. You're going to see that in the coming examples, and then that plot you do will help you to know where you sit in terms of whether for acceleration, whether for velocity, or for displacement. So the last case we're looking at, it is the acceleration response factor. This one here, which is RA. Now, as you can see from the graph, when your frequency ratio is 0, the RA will be 0, which is same as the velocity. When your curves for the acceleration response factor will be peaking just above when the frequency ratio passes the 1 unit, where the ratio between forcing frequency and natural frequency passes the value of 1, then it will start peaking. That's what we mean. It's just after 1 you will start peaking this value. Now, someone will tell me, does that really matter? It's just giving us, yes, as a final value, it won't really make a much difference, but it will help you to know which curve you are looking at. So again, that will let you distinguish between a velocity curve, displacement curve, and acceleration curve. The displacement curve, the peak usually before the 1 value of frequency ratio. If it's on the 1 unit frequency ratio, if that's where the curve was peaking, then you should be able to recognize it is a velocity response. Acceleration response, it is to do, or it will happen after the 1 ratio between the forcing frequency and the short frequency, right? And same thing with infinity. As we take the frequency ratio to infinity, it will not now start going to 0, it will start going to 1. So that means when your forcing frequency is getting way, way, way higher than the natural frequency of the structure you're assessing, then you won't have any difference between the dynamic response and the acceleration response. And that's what we talked about. If you can apply a shock with very, very short period, you may not feel it because it's too strong, because the ground has moved very fast. won't really affect the structure. We're talking here about we don't have face these issues in real structures, but you can imagine if something is beyond. I think you know, like sometimes why we can't see the you know, some of the communication waves, yeah, why we don't see them or why we can't hear them, because their frequency, they are much higher what your ears can really absorb. So that's kind of the same concept. We don't have these applications in buildings because earthquake won't be that significantly happening with very high frequency ratio. We're going to be somewhere within logic, sensible responses. But yeah, you can't think, because someone will say, does it mean if we really have very high frequency or reaching infinity, does that mean we won't be affected? Yes, that's what happening with all the infrared and other telecommunication waves we have around us, like Bluetooth and all those waves. We don't sense them because their frequencies are very high. All right, so that was just a snapshot through the frequency curves I've given you last week, but last week we only talked about the deformation parameter. This week I'm repeating what we showed you last week for velocity and for acceleration response. Is there a question? Just hearing some sound there. Can you hear me, guys? Can you confirm you can hear me?
Yes, we can hear you. Sorry.
Excellent, thank you. All right, so in some plots, to simplify things, and these data, as I'm going to take you at the end of this topic, you may, as I said, we're going to be practicing these things on buildings. All right, we may be practicing these things on buildings, and in week 8, around week 8, I will ask you to generate similar, not same, but similar plots for buildings, and you're going to see how we use them and how you're going to assess the sensitivity of buildings against different type of earthquakes. You're going to be doing same kind of concept in plotting these curves for real building applications. But sometimes to simplify things for engineers, they put all the 3 parameters in one graph. Okay, three axial presentation. Now this it's very easy to use, and you're going to be using it. You're going to be using it. Some of our examples that will happen in week 8 or so. Now you won't be able. We won't be applying it when I'm going to ask you to develop it. You won't be able to do it by Excel because you need special softwares to do that. However, the ones I will let you use, they are kind of made from a textbook, and I will let you use it. But what I'm trying to share with you here is you will be, for example, maybe beside the buildings, you may be doing research in dynamics, and you will be buying some accelerometers. Those devices I mentioned to you, we use them to measure displacement. They call them accelerometers. Now, those displacement sensors, they come up with kind of these charts that will help the users to know when they're going to reach frequency, when they're going to be, and what's their response values, which is very useful for you, because when you do experiments, you need to make sure the harmonic motion you're going to apply gonna be traceable. So you have to, you know, set up your experiment in a way where you would make your structure get excited and maybe get it to reach resonance. So how you're gonna determine those values, you need to make sure your displacement sensors or accelerometers will actually be able to measure this as well. You can't just apply values without making sure your measuring device can actually read it. So what we do, we go and read those manuals from the accelerometers, which will typically give you such graphs. So what I'm trying to say, where we use these kind of graphs is usually when we buy or purchase some dynamic measuring tools, or if you like the traffic engineers who are going to be assessing the vibration for a bridge, they usually work with those charts because the equipment they use, they are defined with such charts. And again, that will help those engineers to determine what range of vibrations they can set their machines to work at. Okay, so that's kind of one of the uses. And as an application in the subject, we're going to have similar chart, not same, not exactly same, that we're going to use to assess the building behaviors. Okay, so basically they plot the velocity and acceleration and displacement all together in one chart. And the frequency vibration or ratio is actually there as well. How to use it if for example, this chart basically, or this axis, you can take whatever value from here to go towards the plot. And remember, each curve here, each bell shape is represented by a specific damping ratio. Then let's say your structure got 20% and you have applied with the test, you have applied a frequency ratio of 0.6, let's say. I mean, 1.25. So you're going to be, or actually this is 2, let's say 2 as an easy number. Let's say 2, then you're going to take your measurements vertically until it hits we said 0.2, didn't we? So it's somewhere here. That's where we hit the curve 0.2, damping ratio. Then from here, you can calculate all the other parameters. Remember, we had mathematical relationship between all those three guys. Here it is. Now, instead of using the formula, you can use the chart, because the chart can be done with Excel and some data calculations. You can do them for a range of frequencies and a range of velocity and a range of acceleration and a range of deformation. So as I said to you, by the way, you're going to be doing something like this, but not for small equipment. You're going to do it for a building. So after we plot all those data, you will be now able to say whichever frequency you want to set up your test with. If you ended up with 2, you're going to go all the way up. And by the time you hit that curve, we hit this one because it's the one with 0.2 ratio. So it's going to be somewhere here again. Oops, should be super vertical like that. Then this, from here, you can read the displacement like that. I can read the displacement, which is about 0.5 of whatever the unit is. I don't think the unit is mentioned in this curve, but we need to make sure. Remember, this is a ratio, so we don't have a unit, because RD is the ratio between dynamic over static. So there is no unit actually. If you keep going this way, it's going to be also 2 for the acceleration. And if you keep going this way, you can get your velocity as well. So you see, with 2 lines, you are able to measure up. Sorry, I think I miss. So again, let me explain this again, because I think I showed you for one value. I will use red for the velocity. For the velocity, you're going to go upwards vertically. By the time you hit the curve in subject, you take a horizontal line, right? This will measure velocity. For the acceleration and displacement, you go same thing. By the time you hit the same point, you have to go, I think I did not, you have to go vertically. Maybe I did not mention that to you. You have to go vertically on the, I'll just delete this. So by the time you hit the curve, you have to go with a vertically or with a 90 degrees on the axis. The axis I'm talking about here, this should be 90 degrees. The axis I'm talking about here, it is the deformation. So that's what our measurement is, which is here. So it's actually not 0.5. It should be less than 0.5. So we got 1.2, 0.35. So it should be 0.35. Okay, that's the ratio, RD. Acceleration, same kind of technique. By the time we hit the curve, let me do it with this color. By the time we hit the curve, we should go vertically towards the acceleration axis. We go like that. And that will give you perpendicular. And this point here will be, so it is 0.5. And here is 1. That's 2 is here, so 0.15. 1.5. Right? So 1.5 is your acceleration, RA. It is the acceleration response factor. So that was just letting you know how we use those graphs. You basically hit the, and remember, you can go from different ways. If you have the velocity, you can start same thing. Already, you should aim at hitting the curve. From that point where you hit the curve, you should go perpendicular on each axis, and that will give you the measure. Not sure if you used it before in different application, but that's how we work with these three-axis curves. Now, we will apply this in some examples, but it's on a different topic where I will ask you to plot them for building excitations. And you're going to be using them to evaluate the building you're working on now as well. And I'm going to ask you to do it dynamically. Any question about this curve or any further clarifications? So what we did here, the three properties I took you through: deformation response factor, acceleration response factor, then velocity response factors. They all can be plotted in one graph. And the way we use them is after we determine the point on the curve, you have to go perpendicular on each axis. So, right. Now, there is another mathematical use and function that we will apply in some of our examples as well, if not today, maybe during the workshop. This is coming from what's called half power bandwidth. So engineers who've been working with those curves. So this is just one of the curves for a special case, but they found there is kind of a common reflection or a common behavior in all of those frequency curves we're talking about. So in this case, we got the ratio, the frequency ratio on the horizontal axis, while we got the deformation response factor on the vertical axis. And what did they found? They found there is a typical well-known relationship between this level and between this distance. So this distance, which is defined by this point and that point. So what they're saying is at resonance, if you go at resonance, which is where the curve is peaking, so at the point of resonance, what you can do, you can plot a horizontal line. That horizontal line is defined at 1/2 root square, yeah, of the peak. So if you go now and take, this is number 5. If you multiply this number 5 by 1/2 root square, it will give you about 3.5, right? So they're saying if you take a horizontal line, which is about 1/root square 2 from the peak, which, as I said, if you go now multiply 5 by 1/, which is about 0.7 something, 1/root square 2, then you will define 2 points, the one on the left and the one on the right. Now, these 2 points will define the half power bandwidth. They call this range as the half power bandwidth, and they found that this range is typically found to be 2 times the damping ratio. Okay, so engineers who've been analyzing all type of frequency curves that I was taking you through for various ratios, for various damping values, they found there is a common relationship happening between all those 100 cases, whatever they do. They found there is a relationship between the damping ratio and the peaking value of the RD value. So first, like we're gonna relate the peaking value for the displacement response factor and the damping ratio. Now, this width is called the half power bandwidth. This may make it a bit more clear. So this is basically the ratio we're talking about. What we're saying is at such situation, we can then find at a frequency, at a resonance behavior when you determine experimentally, or you've been told in a question that the building gonna reach resonance at this much of a frequency. So you can then make a decision and say, I should be able to decide this equation and find such ratio. Okay, and we're gonna have an example which is gonna let you practically apply this relationship and find one of the unknowns, because the band, like omega B or omega B, omega A and omega B, or whichever is bigger, which is omega B minus omega A, can be simply determined from setting this horizontal line, which is basically calculated from the peak of the curve. You just multiply the peak of the curve by about 0.7 something. It will give you this height. When, remember, this is given to you, that plot. This is what you found experimentally. That curve is plotted experimentally. You're going to go to the site and apply some harmonic motion, and you will be able to plot the frequency curve. Now, sometimes we need to find particular parameters, like maybe the natural frequency, it will be, or maybe the damping, whichever you don't have. So you can work in whatever direction, and by determining this level, you will be able, by the graph, you will be able to determine these two lines, eventually these two omegas, and then work out whichever unknown you want. That's it. So again, this section is trying to tell you about the frequency curve, which is known as half power bandwidth. You just need to know it's available there, and it can be used to determine some of the unknowns experimentally. Is there a question we have about the bandwidth? You will see how it's actually used in some of the examples. I'm not sure what's coming next. Right, so that was about the bandwidth. Now we have another kind of topic, which is we're talking about doing tests, right? We're talking about doing tests, and 2 weeks ago we talked to you about doing free vibration test, where you will need to actually displace a building for a couple of millimeters or several millimeters, then release it, and it will be freely vibrating. Sometimes this is not doable. Sometimes you cannot really force a structure to be displaced and let it to free vibrate. So what we do in this case, we can attach what we call it a vibration generator to the floor, right? In case you want to apply a horizontal harmonic motion. So if this was your, say your building, say 3-story building like this, and you want to apply some harmonic motion that will go horizontally, right? Left and right. So what you do at this point here, you can come and attach this system, which I will talk to you about. Eventually, it will end up causing that harmonic motion. Yeah, because these two kind of pans or arms or buckets gonna have weights, and those weights will apply some forces, horizontal forces onto your structure. All right. So the math behind it is, again, this is how they work. Those two buckets, they're gonna not move together. They're gonna move away from each other, typically, where they're gonna end up canceling the force. So when they are positioned like this, right, they're gonna be canceling each other and zero force. Remember, we're trying to generate a harmonic motion, something like this. That's what we're trying to do. So when we are here, when here or there, where we have zero acceleration or zero force, that means the two buckets will be away from each other, canceling each other. But when they're going to be at a position, like when they start flipping this way as shown, they will start causing some sort of excitation into the structure. That excitation will be at its ultimate, or it's at its peak, when both of the masses are aligning together here. Okay, so that's basically the concept behind it. And mathematically, you simply can go and put your free body diagram. That's where you're going to be having this mass and this mass. They're going to be just same, and usually each mass going to be half of the total mass or the total force applied onto the system. So these are the applied forces, and these are the resulted forces. And you can see it's going to end up with a sine function, because that's again what we are after. We're after harmonic motion. It's going and coming. Now, so we from applying statics, simply you can end up formulating this equation of motion, if you can call it, and then this one will give us, if we apply this, so this is back to the equation of motions we talked about in week 3. Here, the forcing excitation, it is for the generator we're talking about, going to be defined with this function. So the function we had for today, or for the vibration generator, it's going to be as shown from applying statics on the free body diagram we had from this graph. So we end up with this relationship. And then what we can do here, we can again do all the math behind it. You see, because we have a differential equation, the final answers for the equation is ended up defining the displacement, the dynamic displacement, and the acceleration displacement. So the dynamic displacement basically is given by this equation, which is the UO. We talked about this property before. It's the dynamic, or the dynamic deformation or displacement, and this was the acceleration displacement. Now I've put for you the parameters which we mostly used in our engineering problems. So as I said, dynamic engineers will be very interested to determine if they use this machine or that generator on top of a floor. They want to estimate the level of displacement. That's basically one of the key criteria we want. Acceleration is also important. It is going to give you the force that you're actually putting on that floor. Velocity, I didn't put it here, but you can still see it's a abbreviation from the textbook, but it won't be used in our examples. That's why I did not present it to you here. But simply what you're doing here, using math and solving for the deformation, then solving for the displacement. Remember, this is only applicable for the cases where you use the vibration generator. You can see here as you go, as we're going over from week 3 up to week 6, only 3 weeks, but there are different ways of calculating things. And when I see some students, like I've asked you some questions to go and calculate acceleration or displacement, and maybe we're talking about free vibration. In the exam, what they do, they come and use this one, but this has nothing to do with the vibration generator. So you just need to make sure you're using the equations and the problems. Okay? And if we got the generators in the questions or the problems, then these equations, equation 20, will be applicable, because it was driven from this equation of motion, which was already set up for the vibration generator. Now, the peak force, which I was saying, when the two masses going to be working together, they're going to be both of them standing here, pushing the mass, whichever direction, downwards or upwards, then the peak force will be calculated by this formula. Okay. Now, one of the interesting things you may need to know about the vibration generator when they plotted when they plotted the frequency function, the frequency ratio function, which I've been talking about from the start and last week. They found something different than what we found from normal harmonic motion. So from normal harmonic motion, right, what we have here, because remember here, the harmonic motions is not coming from a mass that we apply by, in theory, we apply this kind of curves. It's not coming from a mass. We're just assuming it's just applied forever. Now, if you remember here, you have a look. Usually, whenever the ratio goes to infinity, we either going to be reaching 0 for the displacement or velocity case, or we will be tending to 1 for acceleration. The special behavior we have about generators is with this curve or with this ratio, we're finding that the acceleration will be actually developing more and more, because it's making sense, because in our case here, we have control on the mass. And whenever you actually put more mass, things will go higher. So it's in function of the mass. That's what it's saying. Because with the theories we were looking at, there was no mass involved in the equation. But now we have control on adding the mass in the buckets. Okay, in this case, they're saying your frequency curve will be amplifying as you go further with your frequency ratio. So as the frequency gonna be increasing, you should expect higher and higher acceleration, because they assume you're gonna be increasing the mass. So that's really why it's happening. And if you look at the math, if you want to see or observe the math behind this, it's all coming from this equation here, the one that we were talking about. So again, this equation here, you can see the omega as well. It is powered to a square. So you can see it's very sensitive to omega, which is eventually the forcing frequency in this case. With the vibration generator, it's heavily in function of the mass. When the mass increases, the frequency is going to increase, and it's not just increasing by a normal amplification; it's just increasing with the power too. So it's an abrupt increase. So that's why you're typically going to have this response, unless you remember in the real test you're going to have those values. So you will always be at specific, maybe 2, maybe 1, depends on how much mass we're using in your experiment. But in reality, we don't really want to, when we do a test, we will study the structure, we will see what is limited capacity, and we're going to go with the good safety factors. You don't want to break the building that you're testing. You're always going to apply frequencies and mass, which will be way below what's going to break a building reasonably. So don't expect you're going to go take your machine and keep throwing masses in the bucket, or use like special weights. You're going to be doing some hand calculations and figuring out preliminary calculations that will tell you at what level we're going to be within safe concentration. So again, that will be depending on the stiffness, etc. Okay, so that was really about the the vibration generator. This slide here basically is kind of telling you why we're doing the vibration generators, which I've just said to you. Sometimes we have to excite a building with frequencies, harmonic excitations, because we are not able to apply free vibration tests. And whether free vibration tests or harmonic excitations, they both going to help us to understand the building more. For example, we will be able to measure the actual important structural properties that I was talking to you about. We will be able to determine the natural frequencies or damping. This is all going to help you to write a report about the health of the building and what type of action can withstand the actual properties of the building. So that was basically what we are doing. Right. So Another way, and another way of using those curves, it is what we call it resonance test. So we're talking here about how the vibration generator can be used. So what we do, which I mentioned to you just before, we apply different acceptable frequencies that will not break the building, and the aim from there is to plot this curve. So this is again what I was talking to you about before. This is one of the frequency curve and depends on a response amplitude. We don't know what's this going to be, whether acceleration or displacement, right? It's up to us. And then we use that half bandwidth approach to find for the unknowns, right? To find for the, we just showed you a relationship between these parameters and the damping ratio, which was here. That was just before talking about this one, right? So we're going to use the vibrator generator, the vibration generator. We attach it to a building. We're going to do maybe 20 tests, and you're going to be measuring the response of the structure. So you're going to be taking different points, yeah, and you're going to end up connecting the points and plotting this curve. Then from that curve, you will be able to answer several dynamic questions or determining several dynamic properties to, and that's what we're talking here about, maybe plotted directly from measured data, depends on what we're looking at. Okay, I think we talked about this item here where we said with the vibration generator, we can sometimes have our amplitudes or responses increasing significantly as we're going with more and more frequencies. So that's why we have to be careful in determining what setup properties we have to use when testing a structure. Again, we're still talking about the frequency response curve and how it can be used alongside with this equation 23, which we used before, to find various unknowns. For example, maybe you need to find the damping ratio. From the curve, you will be able to determine straight away the natural frequency. And from the curve, you will be able to indirectly find frequency A and frequency B, which is the left-hand side and the right-hand side frequencies. So first, you need to experimentally do the experiment, find the frequency curve, then plot the frequency curve, then try to find specific properties to help you do other activities. So we have a very simple example to do here with its own solution. And I will let you just to go about it and read about it. Okay, while you do this, maybe we have a 10-minute break. Just read the question, go through the very simple steps about the use for the half bandwidth equation, this one. And yeah, let me know if you have any questions, but I will come back and continue from there as well. Maybe look at it, maybe what, 3:05, just 10 minutes break. Then we will continue from there. Okay, that's 3:06. And we are talking about example 6.1. So what do we have there? Well, that was the same frame we kind of discussed a few weeks ago, which was also under vibration. And we have estimated some dynamic properties from the vibrations. But what we did here, it was mounted on a shaking table that can apply harmonic bass motions, which we are talking about this in last week. And, with the user can control the amplitude and frequency levels, which is obviously what we want to do because we want to do the plot for various properties. At each set frequency and acceleration amplitudes of the table, there is kind of accelerometer you see at the top here. This is the accelerometer I was talking about. So accelerometer is connected at the top to measure both the acceleration amplitudes at the base level and at the top of the frame. And they were recorded so in order to be used to plot it. The transmissibility, so what does that mean? It is just basically gives you a ratio. So what we're plotting here, just another presentation for the, instead of presenting that curve, just to complement the story, and instead of plotting an RD or RA to come up with more kind of related factors to the experiment we're doing, we're using transmissibility here. Transmissibility basically just taken as the ratio between the frame displacement and the acceleration at the ground. So just the ratio between the acceleration at this level and the other acceleration at the connection level or the base of the frame, which can be also related to what we're doing in terms of the RD or the RA values. So the TR, the transmissibility ratio, is plotted on the vertical axis from the experiment and for various frequencies. These frequencies were basically controlled by the user or by the person who's doing the test. Now, this is the curve that we got. You can see as they moved through the various frequencies, they started with about 3.3 and kept increasing the frequencies. Then they found that the transmissibility starts reducing, well, which will give you straight away a sense that we have gone through the resonance. And that's basically what you want to aim for. As you're doing tests, we're going to be plotting the RD or RA values. In this case, we're plotting transmissibility. So as we plot them, we just want to see when the curve has actually started decaying with its value. That means we have already reached the resonance behavior and we start. Sometimes you kind of feel the system is shaking. If we're talking about testing a floor, you can sense, like you can see high vibrations or high displacement within the floor. But again, the sensors will tell you the exact figures. So basically, the plots are done. And from the plot, they wanted you to find the natural frequency and the damping ratio. So can someone just tell me, both people who are with me online, frequency, what's the frequency here? How you can determine the frequency from the view I'm showing you? From the view I'm showing you for the curve, how you can determine the frequency, the natural frequency of the frame that we tested. My question simply is, by looking to that curve that I'm sharing with you, are you able to tell the natural frequency? What is the natural frequency? Where do you think the natural frequency gonna happen? natural frequency will happen at resonance. And where is the resonance? It's here. So the answer I was waiting for basically is just here. I know it's written on your sheet, but I just want you to be a bit more. So the natural frequency is just, you can read it straight away from the graph. It's here. Now, the second question, the question is after, they want you to find the damping ratio, the eta, which is to find it from the given information. Remember, this is not given to you. This will not be given to you in the question. This will not be given to you in the question. But you need to know about the half bandwidth principle. And in that case, you will need to work out the 9.05, right? Which is, again, the amplitude divided by √2. And then it will give you the 9.05. Then as you set your horizontal axis, you will be able to determine FA and FB. And FA, FB will help you to determine your damping frequency. All right. So step 1, you just need to read it from the graph. And step 2, you just need to apply the half bandwidth concept, which is applicable for all the frequency ratio curves. Now, based on what we've been talking about and based on what we've been teaching you in terms of harmonic motions are not only applied on buildings where we can excite them with harmonic motions, they can also be applied on traffic engineering problems, something like what you see in this example here, right? So sometimes you have an old bridge, that bridge have been curbed and creeped, so it will be sagging over its spans, and they want to really work out, is it safe for the vehicles to drive over the bridge with particular speed limit? Maybe it will start becoming a bit dangerous for the cars to travel with 110k, the maximum speed we have. For example, in Victoria is 110k. You got some bridges which is outdated. Maybe you would need to evaluate if it's safe or not. If it's not, then reduce the speed or fix the bridge, maintain, make some maintenance to the bridge if it's possible. So yes, these are some of the applications we can see from the principles we've been talking about and sharing with you about. So how it's really working here is, again, we're going to go back to the equation of motion. And in this case, we can consider that the ground is actually causing the excitation, because in examples like this or in problems like the one we're talking about, yes, the vehicle will be moving over the bridge, but because the bridge will be kind of curving with approximate, you see the profile is kind of sine or cosine profile, then eventually that can be a harmonic input into the single degree of freedom. In this case, the single degree of freedom is not the structure, it is actually the vehicle. We're trying to evaluate and assess. And the excitation is coming from the curvature we have in the road. So going back to the theory and the equation that will simulate such problem is, as you can see, equation of motion, we then get equated with negative mass by acceleration, because the load will be, the mass will be applied in a reverse direction. Okay. Now, there is a solution for this equation, which is provided to you in the textbook. And that solution was, again, into a way where it can give us very useful information. We're calling it to be transmissibility ratio. In this case, transmissibility ratio, it is basically between the acceleration we're having on the structure over the acceleration we're having from the ground. So, while the ground is bumpy, while the bridge is actually curving, that will cause its own ground acceleration, which is defined as U double dot GO. And in order to measure the dynamic acceleration resulted on the vehicle, we came up with this, or the analytics, the math that is solved and provided in the textbook, showed us we can relate the ground acceleration with the dynamic total acceleration on the vehicle, or that single degree of freedom system, with such lengthy relationship. So this can be a relationship you can use and apply to solve different examples. I just note that same thing, this equation was found to be also applicable when you want to find the ratio between the ground displacement and the displacement that will be transmitted into the single degree of freedom system, which is the vehicle driving over that bridge. So in summary, the harmonic topic that we've been going through for 2 weeks now can be used in traffic engineering problems, which is the one we're talking about here. As I said, what we have here, it is a vehicle traveling along a multi-span bridge. This is a multi-span bridge. Each span is about 30 meters, and due to long-term creep, it have been resulted in overall 150 deflection at mid-span. So we're saying from this level to this level, we had 150 millimeter sag, right? Because you've got 75 at the support and you've got another 75 at mid-span. So overall, it's 150 millimeter sag due to creep. The roadway profile can be approximated with a sine function and with amplitude of obviously 75 because of what we talked about. We've got 75 here and 75 there. The single degree of freedom system, which is the vehicle, can be approximated as shown, right? So there is a damping system within the car, which we all know about. We all have those suspension systems. They do have some stiffness from the springs surrounding the suspension system, and each vehicle got its own weight, which is very usual. Okay. All right. So what we need to do. Right. So what they're trying to do, they want to find out the quality of the vehicle, or they want to find out what kind of actions they're going to end up having on the vehicle from the road. So they're saying when the vehicle is fully loaded, the weight of the vehicle is 18-20 kilograms. The stiffness of the vehicle suspension system is this much. So we have the stiffness from the springs, and its viscous damping coefficient is such that the damping ratio of the system is 40%. So the damping constant, you know, there is a mathematical relationship between the C value and the eta, and they're saying that for whatever C value we have, it can be calculated that the damping ratio is actually 40%. What they want us to find, determine the amplitude of the vertical motion, right? When the vehicle is traveling at 65 kilometers per hour. So basically, they want you to find the amplitude of the ground excitation when the vertical motion of the vertical motion when the automobile is traveling at 65 k's per hour. So basically, this is, again, we're going to be employing the transmissibility equation, which will give us what basically we after. Remember, this is what we after, and this is given to us because of the situation of the road due to creep. Now, looking to the solution, again, there is some facts which you need to work out based on the condition of the road, and obviously we are able to work out some dynamic properties based on the condition, which I do in the past see some students get a little bit stuck with these ones, but by the time you read it carefully, you should be okay with it. So the vertical displacement, based on the given facts, you can determine that the vertical displacement of the tires or the vehicle is basically defined by this function, right? That's what the ground, remember UG. So UG is the ground excitation. It can be defined by the amplitude we got from the ground, which is the 75. Remember, we got sine curve 75, 75, 75. And this is defined by a sine function. Now, omega and t is not given to us. However, we are able to work it out because we know how frequently this is happening. We know how frequently the amplitude is happening. We're going to see next how all this happening. The forcing frequency omega, it is equal to 2 pi over t, where the forcing period is actually the length of the bridge over the speed. This is, again, can be worked out from the facts given about the bridge and the speed of the vehicle. So we know the span is 30 meters, the speed is 65 km per hour. So basically we need to, if you remember, this is the time. It is the time between two peaks, or the time for the full cycle. Time for the full cycle, basically, it can be estimated by dividing the 30 meters over the velocity, right? Which is explained to you here again. So the one I'm just framing with the black here is just some facts you would need to understand in order to solve this problem. Because I know if I didn't put this black frame, some student will come back and ask me from where you got this, from where you came up with these kind of relationships. It's just simply coming from the facts about the bridge and the vehicle and the speed of the vehicle and the spacing of the columns, which really defining the time period of that sort of vibration. So we all know the speed is 65k, I think it should be kilometers, not kilonewtons. Yeah, so we all know this is not kilonewtons. And then I've converted this into meter per second. That's just a unit change. Then the forcing frequency, yeah, can be simply measured based on what we briefed you here about. Yeah, we are able to set up this relationship because it will end up giving me the vehicle will travel from this point to this point in 3.77 seconds. Okay. Now from here, I should be able to define again my natural frequency. So that was the forcing frequency. On the other side, I have my natural frequency, which is just this root square formula. And it was found to be 8.77 seconds. Now you are at the stage simply where you can directly apply your transmissibility ratio, which will end up giving you the displacement imposed on the vehicle, right? Due to this creep we having in the bridge. It was found to be 90 millimeters. So this is what the question is after, but from there you will be able to determine how severe is this displacement, whether it can be simply resisted by the weight of the bridge, or sorry, the weight of the vehicle or not. Yeah, it is about 9 centimeters anyway. Okay, so I think we do have another questions that will let you think about more parameters that you will see in the workshop questions. Right, so that's just a direct, again, application for the transmissibility equation, which is again coming from the free body diagram and also the harmonic motions we have on such system. All right, the last topic, or the last application we are having to talk about in this topic, it is to do with the measuring tools you can use as a researcher, or you may be using, as I said to you. So this can be, this kind of relationships or applications can be done as a traffic engineer where you want to check the safety for a road. And there can be different parameters to be calculated. By the way, like you can be also asked to find the acceleration, right? You can do same thing. And acceleration will give you the shock that you may have on the vehicles and is it safe or not. Now, there are other cases where I showed you about the vibration generator. Now, what I'm going to talk to you about last is how to apply the harmonic motion concepts on systems like, sorry, I just want to go to the left. Yeah, here we go. Here's this one. I'm talking about this one here. You see, this is an accelerometer. And usually these accelerometers, we need to understand how it actually can transmit the load because they're going to be inside them. They do have different sensors and different kind of mechanisms, which eventually they are based on the harmonic motions excitation concept we'll be talking about this week. So let's have a look. And in addition to that, with the, you know how they measure the earthquake loads usually? So that's what we're talking about, vibration measurements and instruments, like the accelerometer I was showing you, or also the equipments we use to measure earthquakes, not the Richter. Richter is a different kind of unit. It just Richter is very generic unit, which they use in the news because it gives you indication for the energy that earthquake got. Engineers don't work with the Richter by its own. Yes, it shows you how severe it is, but in what we really work with as engineers, we work with the time history data. That's what really let you analyze and study what's happening with the building. The Richter is just the energy that will be imposed from the ground onto the buildings and the level of damage it can cause, right? Now, with these kind of earthquake excitations, there are equipments that will be measuring such excitation, right? And how it's measured simply by using this single degree of freedom system. So inside those equipments or tools or measuring tools, whether the accelerometer I was talking about or the vibration measurement tool for earthquake, it is basically consisting of a constant mass inside it. There is some damping, right? Control that damping level. And there are some stiffeners, which is this, which is the spring. So you can, there's not big difference between what you are seeing here and what I was briefing you about here. Same thing, we have a mass, we have a damping device, and we have a stiffness, and there is excitation. So in what we are talking about here is kind of same, but the excitation here gonna be this kind of a ground excitation, which can have whatever function it will have. All right. So the transmissibility formula that we briefed you about, this one, can be again used on the same concept. And that's what they have. As I said to you, we're talking to you about these topics because you may be the engineer who's going to be working with such equipments. Those equipments will come with tables and charts. So those charts will be kind of writing these kind of equations for you to use. And whatever that machine gonna measure, it won't be exactly how the ground moved. You have to apply some equations or charts to give you the actual motion the ground was moving with. So that's basically where we're coming from. The concept we have gone through today can also be used to show you how an equipment will be reflecting to ground excitation. And from there, if we go and work out a harmonic motion applied on such systems, we can end up same thing. There's a deviation process. There is some functions we're going to be defining that ground excitations with, and we will end up finding the displacement values that will end up giving you the results. And if we find the ratio, it will end up giving you, again, the frequency curve. So those equipments will come up with their own special curves that you can use and directly determine what's the difference between whatever the equipment is recording and whatever was actually applied on the ground. So in terms of applying this, we will be talking about a case where we kind of measuring the excitation from a machine when it was installed on top of a roof, and then we need to figure out whether the equipment are within acceptable limits, because as I said, if your frequency was very, very high, like if you have a frequency which will end up being very high than the equipment's natural frequency, then it won't give you any measurements. So for example, here the ratio is a 3. If you have a ground excitation, which will cause a ratio, so ground excitation means a forcing frequency. If you end up finding a ratio which ended up being 50, this number ended up being 50, you can straight away say, no, this device is not useful for you, because it won't be really giving any sense. It won't be measuring what you want to measure. Maybe that device will have some change, some different switches where you're going to change, and you will end up making it possible to measure such high frequency. So this kind of knowledge really will help you to work with dynamic equipments or measurement tools. And we will have example which will let you apply such curves and such equations. And at the end of the day, you try to find the displacement response, whether as a formula or whether from, you see here, whether from this chart. Because this chart, which is, as I said to you, it can come in a displacement form, in an acceleration form, or in a velocity form, but we mostly use acceleration or displacement. It will eventually end up giving you the dynamic displacement. So there's no difference between what's plotted here and what this equation is saying. Because this equation, again, if you go and plot it, it will end up giving you the dynamic response. And this kind of knowledge can be also applied to devices we use to trigger and measure displacement or accelerations within. I trust the last example we're going to do over the workshop will be talking to us about such behavior. So let's wait and see that example. So in summary, today, I think the key thing that we going through today is you need to understand the 3 motions. You need to understand how we're reading and what's special about those 3 curves, right? So you got the RD. I will talk with acronyms because I believe now you understand me. Understand how RD is represented in this frequency curve. Understand how RV is represented in this frequency curve. Understand how RA is represented in this frequency curve. I'm just giving you a summary because we're done with the lecture notes. Then understand the half power bandwidth, because there are cases where we have to use it and solve our problems. Understand the theory and the equations behind the use of vibration generators. And we had example for that. I think we're going to apply an example Wednesday as well. And yeah, I think yeah, this is all related to the bandwidth example. Understand the application of the transmissibility ratio, which is to do with this example, and how we can find different responses for a vehicle running over a bridge, right? And the very last thing is the harmonic motion concept can also be applied in setting up the tools and equipments used to measure dynamic properties on excited components. So that would conclude our topic for week 6. And let me check if there is anything else. Any questions? Maybe I had some, maybe I did show you some videos about the equipment. Let me show you if I can share them with you again. Any questions you want to talk to me about? Maybe if we got some time to even answer some of your assignment question, if you like. So bring them in. Yeah, so I was talking about the, I think that was to do with the impact test. We're going to talk about impact tests in a different week. I think I showed you this video last week. Try to share it with you again. But that's basically, it is a vibration generator. This is basically a vibration generator, which if you want to apply the force, not vertically, so maybe in this case, they want to evaluate the behavior of the concrete slab. So they want to apply the force or the dynamic or the harmonic motion, to be more specific. They are applying the harmonic motion up, down the page, right? So basically, you would think about doing or using such experimental setup if they want to change the use of the slab, right? For example, this floor was used for residential building, and it was used for about 30 years. And they want to check its stiffness. Now the stiffness gonna change over time, like the concrete strength gonna change. So instead of relying on those old 30 years old structural drawings, you can also perform a test like this. Because as per the examples we're doing, you can see that we can find the stiffness, the actual stiffness of the structure. And from the stiffness, you will be able to see whether this floor can now take heavier loads, because maybe, as I said, they may want to change the service load from residential application to industrial, or maybe they want to use it like I've seen cases where a hospital decided to use one of its floors, decided to put an MRI equipment. The MRI equipment is really heavy and generate a lot of vibration. So they wanted to check whether the forcing frequency from the MRI will be acceptable. So by theory, they found it is acceptable, but that's not enough usually, because the supplier will give you some dynamic properties. And by comparing the forcing frequency with the natural frequency of the floor, you can decide on whether it's going to work or not, because usually those machines that I was talking about, the MRI, are very sensitive to vibration, and if they ended up sitting on slabs shaking a lot over specific amplitudes, they may fail. They may fall down. They may fail and getting dysfunction. So in that case, you would think about doing a decent test. So some setups like this, where you're going to apply harmonic motion and just push down. So they're simply just applying a harmonic motion for different frequencies. So first of all, you don't need to play with the mass, because you don't want to break the slab. As we said, as you go, maybe you're going to end up cracking your floor. So you can change the frequency. You start from 1, go to 1.5, 3, and you're going to be plotting your bell curve. So you're going to be plotting your bell curve as soon as you see your curve is actually, if I go back to the notes, as soon as you see your curve start decaying, that means you're almost heading in the right way, because as we said, the generators will have these kind of curves. So they're going to start having some gentle response. They're going to increase. then they're going to decay, then at some stage they're going to increase. You don't want to go this way anymore because practically you won't be there. This means you have very, very heavy mass, which won't be the situation. Okay. And that's it. So once you plot all that, you will be able to work out stiffness. You will be able to, the first thing you can work out is the frequency, natural frequency. From natural frequency, you can work the stiffness out. You can work the damping ratio out. You can work many properties that will end up telling you whether that floor is actually working or not. Okay. So as you can see, now I know there is a lot of formulas, but you just need to systematically put them down and understand their use. But on top of that, pay attention to the real applications of what we're doing, because as I said to you before, they're always going to be part A or part B or part C question in your final exam that will require you to know the physical meaning of those kind of theories or parameters. Yeah. So, for example, you may be asked which, if you need to place an MRI equipment on top of a floor in a hospital, just briefly discuss which experiment you're going to be doing, and you simply just need to know what we're talking about. So it's going to be kind of a part question for an example you're doing, right? What does it mean if your response was here? What does it mean if your response was decaying? Or what does it mean if your response was amplifying? Okay. Any questions? Any questions about the assignment? You're going to get a full mark there? Is it easy?
Sir? Excuse
Sorry,
me, sir?
I think some people may be talking. Now it's better. Yeah, someone trying to say something? Yes?
Yes, sir. I have one doubt. Our group has one doubt in the assignment. Could you please open week 5 solution PDF, please?
Yes, I will do that. Let me go to LMS and open it. No, that was the workshop question. We need to open this. It will take time. Let me download it. Yes, it's coming up. Which page do you want us to talk about?
In the explanation of case 2, page number 9, sir.
Yes.
Yeah, this one.
Yes.
Here the calculation of G is a little confusing because it's not getting the similar value. How did we consider the calculate the dead load on the wall? the G
Okay.
calculation.
Okay, now definitely don't get misled by this. That was just a sample that I just want to discuss with the students about. But let me show you. So you're asking about the G. And
Yes, sir.
remember, same thing can apply for Q.
Yeah.
But Q don't have the concrete weight. So with G, what you do here, first thing, you got two components. This area, let me just use this highlighter. So this area, do you know how we define this area?
Oh, yes, sir. Using hatch, we measure the half distance between the end of wall to the next,
Excellent.
next element.
So yes, basically you need to calculate this area,
Yeah. Okay.
which I estimated to be about 8 meters squares. Maybe yours is different. And then the dead weight from this area will be basically the dead weight will be 0.2, which is the thickness of the slab, by 25, which is the density of the concrete. That will give you the pressure, right?
Okay. Yeah.
And then once you apply that pressure by, remember here we're trying to find a point force, a force value. Some people may find it as a line load, then convert it to pressure. In the end of the day, by using this formula, this one, I want a force value, a kilonewton value, and then I'm going to divide it on the area, right? So going back to where I was, I will end up for whatever I'm indicating to you, my approach is to find the kilonewton value. So first thing I have the slab component pushing this wall down. So I found the area, then I'm going to multiply the area by the pressure. What's the pressure? The pressure is the thickness of the slab by the density of the concrete, which is 25 by 0.2. That will give me kPa. kPa by the area will give me the force that will come from this piece of concrete for one single level. I will multiply this by 10. That will give me the full load for 10 stories. Maybe here I did not yet multiply. No, actually I did. So I'm not sure. But I was also saying to you here, it's consider the weight. Effectively, we do have also the wall, right?
Yeah.
And the wall, it's kind of same, but the wall is standing vertically. So for one floor, I will find the length. Maybe first thing what I will do, I will again multiply the height. Say the height is about 2.8 or 2.6 or 3. So the height is 3 multiplied by the length, multiplied by the thickness, multiplied by the density of concrete. We said take it as 0.25. And then I'm going to multiply this by 10 times. So for your case, what was the area?
It's 8.3. The hatched area, the supported area is 8.3 something.
That's fine. So 8.3, right? And so what you're going to have is 8.3 multiplied by the thickness, multiplied by the density. That's from one floor, right?
Yes.
And for 10 concrete floors, it will be 415. That's only the slab. And I think that's why I was showing here.
Then what is the 6 kPa over there, sir?
That's a very good question. Ah, that's from the wall. Approximately.
Oh, from the wall.
Let me just. So the pressure again is that's the pressure is 0.2 multiplied by 25, which is the density of concrete. That's the pressure. Okay, I think that's what I'm saying here. So what's wrong here? I'm just saying. Okay, why I put 6 is the one superimposed dead load. Yeah.
Oh, okay.
Yeah, so yeah, there was one superimposed dead load, which gives the 6 kPa. Then I multiplied by obviously 10, then I multiplied by 8, and in your case it was 8.3. So yeah, it's giving us same numbers, but here I think you can count, count for wall load and roof load as well. So that's what I'm saying. I did not show the students here how to put the weight of the wall, but you have to, because if you did not, you're going to find some major discrepancies between RCB and this hand calculations.
Okay.
Did it make
So
sense now? But yeah,
yes, sir.
basically the 1 kPa was coming from the superimposed dead load.
Okay. The dead load on
I
the wall
think
plus the superimposed dead load times 10
yes,
floors into the area of the supported region.
correct. And also add the, so that was the superimposed dead load.
Yes.
And also add the wall weight. Yeah.
Yes, sir. Understood. Thank you so much.
That's all. Okay, good. Any questions about what we're doing here? Does it all make sense? So that was this page and that one. Those 2 pages, they were just clarifications for the students for one case only, for case number 2. But yeah, this should have been repeated for all the directions, all the cases. Okay, so yes, Rashid.
Sir, can you explain the part that you have showed, like the billing one, the wind part?
Which one?
The MB NW?
MB. This one?
Yeah.
So you want to know what we are doing here?
Yes.
Yeah, so basically what I've briefed you about on those slides, that was for case number 2. And I'm briefing the students here. Let me open my laser before I mess up my sheet. Yeah, we do have about 5 minutes there. So basically, I was just briefing the students about how to combine the stresses together. But I have given them an example on those 2 pages. Now, remember here, these stresses need to be calculated by using formulas. Depends on whether it is a bending stress or an axial stress. In this case, it's a bending stress. That's what the situation we have. When this wall gonna be pushed in this scenario, the wind gonna be flexing the core. So we have to use bending stress to find the tension here. And because we have dead load, which the student was asking me about, which is 90% of that dead load can actually help to push things down, right? And that's why, but these stresses, they are axial stresses. Right, stop me if you are still, if you need question. So what I was saying, for this bending stresses, we have, or we can, or we should use this formula. Now you can see bending stresses is a function of properties I ask you to pre-calculate, and it is a function of the moment value at whatever level we want to assess the core at. And that's really what I'm showing you here. Maybe some students, they will say, what we are doing here. Simply here, I'm just using statics, right? To calculate the bending, the total bending at the base of the building. Now, as I was investigating the wind case, I have to go to the north winds. All those forces are simply the north winds I took from the table I was asking you to do for about 3-4 weeks. And I put them on each floor. Then I use simple statics. You know, to find the moment around this point, you multiply force by distance, force by distance, force by distance, etc., etc., etc. And I didn't do that. I just know the 120 will be multiplied by this height, plus this height, plus this height, plus this height, plus this height. Yeah, it's just so this number here, 143, is just our cumulative calculation for the height. If you want to do it piece by piece, so be it. It's just going to be right. Now the last figure here, 75. I separated it from there because it's got different force, obviously. That's why I couldn't add it within here. So I ended up calculating here the banding which I need to use in this formula here. Remember here, I'm talking about the case 2 only. So once I'm ready with my moment, I just put it aside and I said also let me go and calculate the dead load, because I have to have axial load, the dead load, and that's what I was talking with the other students just before. And yes, here we don't need wind. We will not be using wind life load here, because life load will be actually helping us. The life load here, the life load will be basically helping us, and I cannot guarantee. That's why in this formula I did not introduce any life load, because someone will ask why you didn't also compress this side by life load. I cannot guarantee people will be standing behind the core during when the wind gonna blow. So that's why we have to use our engineering judgment. It's only the dead load, and I took 90%. That's what the standard told me, because definitely 100% the concrete is there, day and night. Okay, so that's why for this case, I've only calculated dead load. I'm not calculating life load. So these green frames, you know, this green frame, this one, I'm just preparing my actions to put in the equations. That's all what I'm doing here. You can see here that I'm showing you on this slide how I calculated this and how I calculated that. This one, simply by the same formula I keep talking to you about. And to calculate the axial stress, I'm just using this very simple mechanics of solid equation, which is the force over the supported area over that wall and subject. Here, this line is showing you how I substituted the values, right? So this is the moment when, what was it? Let me check. Yeah, it's same as this. This one, I just took it here, and I've just changed the units. 850, it's basically this distance, which you measured from CAD. You need to show me all those details in your report, right? And that was why. The inertia, I also measured from CAD, and I put it here. Is it making sense?
Yep.
Okay. Then this side, it's basically that one here. I'm just continuing. Yeah. And yeah, I ended up finding the tension. No problems. Okay, so I think we will have some good time during the workshop. Just keep asking, keep you going with the project. Right, it's 4 o'clock. Let me stop recording, and we'll see you guys in 2 days, online or face-to-face.